large language models.
You've probably, typed a question into a chatbot, maybe let AI finish your sentence for you. Or perhaps you've seen some of that really wild art it can generate from just a few words. It often feels a bit like magic, doesn't it? Almost like these things understand what we're asking. But have you ever really, stopped to wonder what's actually happening behind the curtain? Today on the deep dive, that's our mission. We want to peel back those layers. We're going to explore the fascinating world of large language models, LLMs, to really get a grip on what they are, how they're built, and what makes them tick. We're aiming to cut through the hype, get to the core knowledge so you can be genuinely informed about this incredibly transformative tech.
That's exactly the goal.
Yeah.
At their core, large language models are really sophisticated language programs. They're trained using this technique called self-supervised machine learning, and it's done on just colossal amounts of text data, billions, maybe trillions of words, their main job, processing and generating natural human language. When you hear about the most powerful ones out there, the ones driving today's big AI chatbots, you're very often talking about generative pre-trained transformers, GPTs. That transformer bit is not just a cool name. It points to the specific kind of revolutionary architecture they use.
Okay, let's unpack that a bit because it seems like magic, but you're saying the core idea is actually pretty simple. Next token prediction. It sounds less like understanding and more like, well, being an incredibly good guesser. But if it's just guessing the next word, how does it write a whole essay or code? That seems like a bigger leap. There must be something else going on, right? Some secret sauce connecting those guesses.
You've nailed the core mechanism. The basic idea is, yeah, the LLM takes a pre-context, everything it's seen so far, like, I am a machine. And from that, it predicts the most likely next token. Now, a token could be a whole word, or sometimes just part of one. So in your example, I am a machine, it might predict learning as the next token. This step-by-step prediction is called autoregressive prediction. That's how they build up text, token by token. Think of it like super advanced autocomplete, but one that considers context across huge amounts of text it's already seen. Now, during training, this guessing game becomes what we call a supervised learning problem. You feed the model countless examples. Here's a context, and here's the actual word that came next in the real text. And the model constantly adjusts its internal numbers, its parameters, trying to make its prediction match the target. It's always trying to minimize its mistakes to lower this score called a loss function, basically getting less wrong over time. But how do words become numbers for the computer? Well, the text gets tokenized first, broken into those chunks we mentioned. Then these tokens get converted into numerical embedding vectors. So each word or token, and critically its position in the sentence, gets its own unique string of the numbers. It's these numbers the model actually processes. So when you ask, is it apple or banana next? Well, the model isn't seeing words. It's processing complex numerical patterns tied to those words and their context.
Right. So if it sees the quick brown fox, it's running the numbers on maybe thousands of possible next words, calculating the probability for jumps, eats, sleeps, whatever's in its vocabulary, and then picking the most likely one. Okay, that's clever. But just predicting the next word still doesn't quite explain how it seems to understand grammar or meaning. It needs to grasp the relationships between words, right? And that's where the brain comes in, the transformer.
Exactly. This is where things get really interesting. The brains, as you put it, of almost all modern LLMs, including models like GPT-2 that really made waves. It's this thing called the transformer architecture. It came out of Google Research back in 2017, and it wasn't just a small step. It fundamentally changed NLP. Its power comes from stacking these units called transformer blocks on top of each other. Each block refines the understanding. And inside each block, the key mechanism is self-attention. Let's say the model reads, "The quick brown fox jumps over the lazy dog." When it processes the word jumps, Self-attention lets a look back at all the other words, fox, brown, dog, the ick, and it figures out how important each one is for understanding jumps in this specific sentence. Is fox more relevant than lazy? Probably. It's like assigning weights, focusing attention. It builds this rich web of connections, understanding how words relate within that context, not just in sequence.
Okay, so it's weighing the importance of other words.
Yeah, and then you have multi-head attention. Think of it as having several self-attention mechanisms running at the same time, in parallel. Each head might be looking for different things. Maybe one head focuses on grammatical links, subject-verb agreement, that sort of thing. Another might focus more on semantic, meaning like figuring out if bank means a river bank or a money bank based on context. By combining all these different viewpoints, the model gets a much richer, more nuanced understanding.
Makes sense. Multiple perspectives.
Right. And there are other important bits in the block too. Layer normalization helps keep the data stable as it flows through. And residual connections, they're like little express lanes. They let important information bypass some processing steps, making sure the signal doesn't get lost or diluted in very deep networks. Helps with training these huge models. And one more critical detail, especially for models like GPT that generate text: masked self-attention. During training, when it's predicting the next word, it's crucial. Can't see the words that come after it. It can only look back.
Ah, so it can't cheat by looking ahead at the answer.
Exactly. It wears blinders,
Yeah.
essentially. This forces it to genuinely learn how to predict sequentially, building text left to right, like we do.
So it's this really sophisticated pattern matcher using attention to grasp context. Okay. But how does all this complex architecture turn into something that feels so knowledgeable, so fluent? It must come down to the training, right? The scale of it all.
That smartness really comes down to two main things: the sheer volume of data and how carefully that data is curated. LLMs are trained on, well, almost unimaginably large data sets, hundreds of billions, sometimes trillions of words. Sources like Common Crawl, that's billions of web pages scraped from the internet, plus Wikipedia, huge book collections, even code repositories.
Wow. So basically a huge chunk of the internet and literature.
Pretty much. Yeah. GPT-3, for example, got something like over 80% of its training data just from Common Crawl. The goal is exposure. See language used in every possible way. But quantity isn't everything. Data quality is key. So there's a massive data pre-processing step. Cleaning out junk text, removing duplicates because you don't want the model just memorizing repeated phrases or row. And also privacy scrubbing, trying to remove personally identifiable information. It's a huge job. Though interestingly, some models like Llama 2 actually tried less aggressive filtering, finding it could sometimes help the model generalize better. So there are different approaches.
Right. And we always hear about the cost. Training these things costs millions. Why so expensive? What makes it such a heavy computational lift?
The cost is driven by the sheer number of parameters. These are the internal knobs the model tunes during learning. GPT-2 had 1.5 billion. Newer models have hundreds of billions or even trillions. PAL-M, with 540 billion parameters, reportedly cost something like $8 million just for training.
Just the training run.
Just the training. And training is much more computationally intensive than just using the model later for inference, like asking it a question. Maybe 6 times the computation per parameter per token for training versus just 1 or 2 for inference. So to handle this scale, you absolutely need parallel training. You can't fit it all on one GPU. One way is data parallelism. You put a full copy of the model on multiple GPUs, split the data between them, and they all learn in parallel, then sync up. Another is model parallelism, where you actually chop up the model itself. Different layers or parts of the parameters live on different GPUs. Each GPU trains its piece.
So you're splitting either the data or the model itself across the hardware.
Exactly. And then you have even more advanced stuff like Zero. It cleverly partitions not just the parameters, but also the gradients and optimizer states across GPUs, trading a bit of communication overhead for massive memory savings. And pipeline parallelism sets it up like an assembly line. Different layers of the model sit on different GPUs, and the data flows through them sequentially. It's complex distributed systems engineering.
How do we then get them to actually, chat with us, answer questions helpfully, reason through problems? It feels like there's another step beyond just predicting the next word to make them useful, interactive tools.
Absolutely. That next phase is crucial. It often involves supervised fine-tuning, or SFT. You take the massive pre-trained model and you tweak it, you adjust it, using smaller, high-quality labeled data sets. A really important type of SFT is instruction tuning. Here, you train the model specifically on pairs of instruction and desired output. Lots of examples. This teaches the model to follow commands, shifting it from just completing text to actually responding to requests.
So you teach it to be an assistant, basically.
Yeah, exactly. So instead of just continuing a sentence about Hamlet, it learns to write an essay about Hamlet when you ask it to.
Yeah.
And then there's alignment tuning. This is super important for making models, as the researchers say, helpful, honest, and harmless. The most well-known technique here is reinforcement learning with human feedback, RLHF. It's pretty clever.
Right.
Humans look at different outputs the model generates and rank them. Which one is better, more helpful, safer? This feedback trains another model, a reward model, that learns to predict human preferences. Then, the main LLM is fine-tuned using reinforcement learning to generate responses that score high on this reward model. It learns to behave in ways humans prefer.
So humans are directly guiding its behavior towards being more useful and safe.
Precisely. And for people without giant computing clusters, there are methods like parameter-efficient tuning, or PEFT. LoRa is a popular one. These let you fine-tune these huge models by only updating a very small fraction of their parameters, maybe less than 1%. You freeze most of the original model and just train these small adapter layers. It dramatically lowers the cost and memory needed.
Making it more accessible.
Hugely. It democratizes the ability to adapt these powerful models. And finally, there's ongoing safety fine-tuning. This involves deliberately training models on tricky or harmful prompts, teaching them to recognize and refuse unsafe requests. It's a constant effort to make them more robust.
Okay, so they're trained to follow instructions and be helpful, but you mentioned reasoning. Can they actually think? When I see one solve a math problem step by step, it feels like more than just good instruction following. Is it simulating thought?
It's simulating it extremely well, and often that's guided by prompt engineering. This is a whole field in itself. Simple techniques like few-shot prompting, giving the model a couple of examples of the task right in the prompt, can work wonders. Or self-instruct, where models actually generate their own instructions to improve their task performance. But a major leap in reasoning came from chain-of-thought prompting. Just adding a simple phrase like, "let's think step by step," to the prompt encourages the LLM to break down the problem. It outputs its intermediate reasoning steps before giving the final answer.
Like showing your work in math class.
Exactly. And this simple trick dramatically improved performance on tasks needing logical steps, like math word problems or logic puzzles. And now we're even seeing model-native reasoning. Newer models, like OpenAI's O1, are being trained specifically to generate those reasoning steps as part of their core process. It's not just a prompt trick anymore. It's baked into how the model works.
Yeah.
And the results are pretty startling. O1 reportedly got 83% on some challenging math Olympiad problems, where GPT-4o only got 13%.
Wow, that's a huge jump.
It is. It suggests these models might be starting to, structure their thoughts more deliberately, plan their solutions. It's moving beyond just pattern matching towards something that looks a lot more like strategic thinking. It really pushes the boundaries of how we define intelligence in these systems.
That really is a game changer. It blurs the lines. But with all this power, the simulated intelligence, how do we evaluate them? How do we know if they're actually good
Correct.
or safe or reliable? What are the metrics?
Evaluation is complex, definitely. The classic metric is perplexity. It basically measures how surprised the model is by a sequence of text it hasn't seen before. Lower perplexity means it's better at predicting the next token. And interestingly, lower perplexity also correlates with better data compression. Less surprise means more predictable, more compressible patterns.
Okay, so perplexity is a core measure.
Yes, but it doesn't tell the whole story, so we also use benchmarks. These are standardized tests for specific abilities, things like MMLU for broad general knowledge across many subjects, or HumanVal for coding ability. These help compare models on specific tasks. But alongside capabilities, we have to measure the problems. Algorithmic bias is a huge one. Since they learn from human text, LLMs absorb and can even amplify the biases in that data. Gender stereotypes, racial biases, political leanings, and the fact that most training data is English means non-English perspectives or cultural nuances can get sidelined. It's a serious challenge.
And they can just repeat things they saw in training.
That's memorization, yeah. Sometimes they output text verbatim from their training data. This raises obvious copyright issues and potentially privacy ones if the memorized text is sensitive. It's often an unwanted side effect of the training scale. And then there's security. Prompt injection is a big worry. Users crafting clever prompts to bypass safety filters and make the model do harmful things. There's also the theoretical risk of sleeper agents, hidden malicious functions triggered by specific inputs. Very hard to detect. And a newer threat is LLM grooming. People deliberately seeding online content designed to subtly bias future LLMs trained on that data. It's a potential new vector for disinformation campaigns.
Wow, so influencing the AI's worldview before it's even fully trained.
Exactly. It makes critically evaluating AI outputs more important than ever.
So, given this incredible progress, but also these serious challenges, what's next? What's on the horizon for LLMs?
Well, we'll almost certainly see continued scaling even bigger models. But a huge trend right now is multimodal LLMs. Models that don't just handle text, but also images, video, audio. They can understand and generate across different types of data. Think of AI that can watch a video and discuss it, or generate images from descriptions. That integration is happening fast.
Beyond just text.
Right. There's also a relentless focus on efficiency making training and running these models cheaper and more accessible. That includes PEFT methods we discussed, but also hardware and software optimizations. And while the transformer is king right now, research continues into new architectures. Things like RWKV, exploring RNN-based models, showed that people are still looking for alternatives that might offer different advantages. And one more thing, this field increasingly needs people who bridge disciplines. You need the AI theory, sure, but you also need serious engineering chops to handle the massive data and distributed computing involved. Collaboration is key.
It's moving so fast. So, as these large language models keep evolving, keep getting woven deeper into our lives, understanding what's under the hood, it really isn't just for the experts anymore, is it? It feels like it's about being an informed citizen, really, in a world that's changing incredibly quickly. It makes you wonder, what new possibilities, what creativity, and maybe what new fundamental questions about intelligence itself will these constantly evolving digital minds bring to our doorstep next?